So we're continuing to talk about functions, and today we're talking about continuous functions. So remember last time we talked about discrete functions, and our discrete functions were disconnected. Discrete was disconnected. So our continuous functions that we're talking about today are going to be the opposite, are going to be connected. Before we can talk about those, we need to talk about lines, which are a type of continuous function. So linear equation in two variables, x and y, any type of line can be written in the form of y equals mx plus b. And the graph is a line, which is kind of obvious because it is a linear function. M always represents our slope, and B always represents our y-intercept. Okay, so M is our slope, B is our y-intercept, and they are constants. What that means is that they're not going to change. So like our slope's not going to be 4 for one part of the line and 7 for another part of the line. It's always the same. So a linear function, as a little more specific, is a function whose graph is a non-vertical line, and it is represented by a linear equation. So a linear function is represented by a linear equation. So just like before, remember we learned that so we have, in the world, we have relations. You don't have to write this. We have relations, and then underneath relations are functions. So every function is a relation, but not every relation is a function. So notice that we have linear equations, which is all of our lines, but some of them are functions, and the ones that are functions are our non-vertical lines. Think about it. If you had a vertical line, a line that's straight up and down like this, that's not going to pass the vertical line test because every point on the line shares the same x value. So any linear function has a constant rate of change. You will hear us use the phrase rate of change a lot. So this phrase right here, rate of change, is super important because it's a way to describe slope. This phrase, constant rate of change, we will talk about that over and over and over and over again. It's one of the ways that we define functions or define lines, and it's something we will talk about, like I said, a lot. So a nonlinear function, so obviously if it's nonlinear, then it's not a line. Okay, nonlinear means not a line. And nonlinear functions do not have a constant rate of change, and the graph is not a line because it's not linear. So we've got to figure out whether these equations and graphs are linear or not linear. And if they're not linear, why not? Let's start with our graphs first. So we're going to look first at this one here. Well, remember, if it's linear, then it's a line. Lines are straight. They either go up or they go down, or they could be vertical or they could be horizontal. But vertical would not be a function. But this right here, this graph, if you notice, this is not a line. So this graph is not linear. So I'm going to put a big X over it. I'm going to look at my next graph, which is, when I look at it, well, there we go. Oh, look, it's a line. It's connected, it's straight, so this one here is linear. So I'm going to circle that. Okay. So let's look back at the first one that wasn't linear and ask us why it wasn't linear. And this is not linear because it's a parabola. That's what shape we call this. This funny looking curve that looks like this parabola, this graph is called a parabola. So if I look at this next one, y equals 3.8. It's really helpful to remember what a linear function looks like. So look back up here at your notes. If it's linear, it's in the form y equals mx plus b. And m and b are constant numbers. The biggest thing to note is that x here is just x. It's not x squared, it's not x cubed or anything like that. So if we look at this equation, y equals 3.8, this one, as weird as it sounds, this is going to be a line. In fact, this line is going to be horizontal. That's what this graph will look like. So this one, y equals 3.8, is a function. Y equals 2 over x. Well, if I look at this, notice x is in the denominator, so it is not a linear function, okay? Because x is in the denominator. That's why it's not. So the x is in the denominator. If I look at the next one over here, y equals the square root of x, notice it does just have x, but it has this square root symbol. Okay, if it's got that square root symbol, it's also not linear, and it's not linear because it has a square root symbol. If I look at the next one, y equals 3x, 3 to the x, I'm sorry. Notice x is my exponent, so this is actually called an exponential function. The next one, I'm sorry, it's not really numbered, but this over here, y equals 6 times x minus 1. Well, if I were to work this out by distributing my 6 in, just to kind of help me out a little bit, get rid of these parentheses, 6 times x is 6x, and 6 times negative 1 is negative 6. This right here, this is a line, because this is in y equals mx plus b form. So this one is linear. If I look at the next one, this one down here, x squared minus y equals 0, this is not linear because it has x squared. So that x squared, that's going to make it a quadratic. It's going to make it a quadratic. That's going to make it the U-shaped graph. So somewhere on your notes or on a separate sheet of paper, I want you, and this would even be something good to write on your vocabulary page, I want you to write this down because it's important to note the other types of equations and graphs that you might see. So we have what's called a quadratic, which we did mention that, a quadratic. A quadratic graph is going to be in the form of y equals, it's going to have an x squared with it. So anything with an x squared in it is quadratic, and its graph is a U. It is a parabola. That's what we call it. It can either open up or it can open down, but it is a U-shaped graph. The next type that we could see is we could see a square root. And its equation is going to have y equals the square root of x. It's going to have an x in there. And its equation actually looks kind of like a square root symbol. It's going to be like half a parabola on its side, but it curves off to the side. The next possible equation we could have an what we call absolute value. Absolute value is going to have this weird thing where it's going to have y equals, and it's going to have these weird lines that we call absolute value lines. And their graph, its graph is going to be a V. Well, that's easy because it's a absolute value, so that's V for value. We could also have an exponential graph, or an exponential equation. Exponential is going to be y equals maybe 2 to the x. Notice because it's exponential, because it is exponential, notice this word right here, exponent. X is the exponent in exponential. Okay, that's where this comes from. And its graph is going to look like this. It's going to be kind of like half a parabola. We could also have an inverse graph. An inverse graph is where y is in the denominator. So there's an example of an equation, and its graph is going to look like this. It's actually going to be two pieces. It's going to curve down, and then the other part's going to curve the other direction. It's going to look like this. That's an inverse graph. So those are some of the options. Those are probably the most common that you're going to see 5 apart from linear. Don't forget that it could be linear as well, which we just talked about, but it's probably good to write it down again. So we could also have linear and it's going to be in the form of y equals x, and it's obviously a line. The biggest thing to pay attention to, and the easiest way to tell what kind of graph it is by looking at the equation. Okay, so recall that x squared, that's not linear because it has the square root, that's our quadratic. If it's got the square root symbol in it, that's what makes it absolute, or square root. If it has these lines, that's absolute value. If x is my exponent, that's exponential. If x is in the denominator, that makes it an inverse. And if x is by itself, that's what makes it a line. So going back to the notes, we have one more that we have to do, and this one's a table. And it's a little bit hard to tell in a table if something is linear. But remember, if it's linear, it has a constant rate of change. What that means is it's increasing or decreasing at a constant rate. So we need to figure out how much this table is increasing. So we're going to look at our x's. Well, every time to get from 1 to 3, my x increased by 2. From 3 to 5, my x increased by 2. From 5 to 7, my x increased by 2. Then we look at our y's. Well, from 2 to 9, it went up by 7. From 9 to 20, that went up by 11. And 20 to 35, that went up by 15. So pay attention to the fact that this was consistent. This was consistent. Every time my x's increased by 2. But down here, my y's, one time it was 7, one time it was 11, and one time it was 15. That is not consistent, so this is not linear. That's what that tells us. So what is continuous data? So remember, discrete was disconnected, and so the numbers in the middle didn't matter. Like if it went from 1 to 2, the 1.5 didn't matter. Like thinking about buying movie tickets. You can't buy half a movie ticket. So continuous data is the opposite of that, and it is data where the numbers, so data where the numbers between any two data points, so the numbers between any two data points have meaning. So it's where the numbers in the middle, so some numbers in the middle matter. For example, if you were talking about height, that's an example of continuous data. Because think about it, you don't just jump from 5'6" to 5'7" overnight. You slowly grow from one to the other. So those numbers in the middle matter. Another example is temperature. Another example would be weight. That's another time where those numbers in the middle matter. It's also important to note, I'm going to write this over here, that continuous data is connected. So recall, just remember that our discrete data was disconnected. So this time our continuous data is connected. So it'd be like a piece of yarn is an example of something that's continuous. Okay, it's going to be something that's connected. On a graph, this is illustrated by a solid line or segment. This is illustrated by a solid line or segment. So if we look at the situations and graphs below, we're supposed to write a C for continuous data and write a D for discrete data. Well, number 1, the cost of tickets for a Rangers baseball game, that's going to be discrete data. Because some tickets cost $10, some tickets cost $12, but you're not going to have reason to have all the numbers in the middle. The height of children, that is going to be continuous, because like we said earlier, height is something that is continuous because the numbers in the middle matter. Your weight on the moon versus your weight here on Earth, that is also continuous. So we have some graphs for 4 and 5. 4 is a continuous graph because notice it's just a solid piece right there that's all connected. Number 5 is going to be discrete because it's a set of points. They're not actually touching each other. They are not connected. Number 6 is also discrete data because number 6 again is just a set of points. So notice there is not every value is included in that. It's just those 4 points right there. So we're going to talk about how to find our domain and our range. So to help us out, you need to meet Delore the robot. So this is Delore. So you can say hello to him later. You'll see a poster of him up in the classroom. But this is Delore, and Delore is your friend because he's going to help you remember how to find the domain and the range of a continuous function. So first of all, let's start with our domain. So the Delore will help us remember the domain, and the D, the L, and the R stand for that our domain is read from the left to the right. Remember, our domain, if you'll recall, is our X values. So we'll come back to range in just a second. Remember when we did inequalities, okay, when we do inequalities, with we have open circles and closed circles. Open circles are used with a less than or a greater than, and closed circles are used with a less than or equal to or a greater than or equal to. So for number 8, we want to practice finding the domain, 8, 9, 10, 11, and 12. We're going to find the domain of these graphs, okay? So looking at 8, when you have one like this where it has 2 distinct endpoints, or any time really, for the domain you want to draw a line through the left side of the graph and a line through the right side of the graph. Well, our left side of our graph here, this side, is at -2. So that's where our domain starts, is at -2. And then the right side of our graph over here is at +3. So that's where our domain ends. So we're going to put -2, and then we're going to leave a space, and we're going to write 3. Remember, our domain is our x's, so we're going to put x in the middle, because what we're saying is that our x's, our graph here, is between -2 and +3. So we're writing that x is between -2 and +3. When you write it in this notation, in inequality notation, you always use less than symbols if there's 2 numbers here. And then what we're going to say is that -2 is less than or equal to x, and x is less than 3. The reason we use less than or equal to here is because, look at -2. There was a solid point there, so it's less than or equal to. At +3, there was an open point, so it's just less than. So this is called inequality notation. So if we look at number 9, again, we're going to draw a line through our left side and a line through our right side. So my left side is at -4, and my right side is at +7, and my x's are in between that because my graph is in between. So at -4, notice there is an open circle, so that means we're going to put a less than. And notice at +7, it's a filled in circle, so that means we're going to put a less than or equal to. For number 10, it's a little bit different because when I draw my line through my left side, notice there is no right side because it just keeps going forever and ever and ever and ever. Okay, so when it's like this, where x's doesn't have a start and a stop, I'm just going to put x and my number, which would be -5. That's what point this was at. This was at -5 here. So which direction is this going? Well, this is really easy. Look at the direction your arrow is pointing. So this tells you right here that your sign is a greater than. And because this dot is closed in, then it's going to be greater than or equal to. So those are my domains based on those number lines. It doesn't change when I look at a graph. Like if I look at 11, 12, and 13. For my domain, I'm still going to read it from the left to the right. So I find my left and my right of my graph. I draw my lines. Well, my left side is at -3, and my right side is at +3. Since it had a start and a stop, I know I put X in the middle. If I look at -3 here, it's an open circle, so I'm just going to put a less than. If I look at this +3 over here, notice this circle is closed in, so I want to put a less than or equal to. Well, there's my domain. So for number 12, I'm supposed to draw a line through my left side and my right side. So my left side is here. Well, that's easy enough. But notice that my right side just keeps going. It goes on forever and ever and ever. It doesn't actually stop. So that means I'm just going to put 1x, and I'm just going to put my number, which this line over here goes through the point at -2. And my arrows are pointing to the right. So that tells me it's a greater than sign. And on these, what you have to figure out, there's no point, there's no dot there. But you have to ask yourself, does the graph actually touch at -2? And it does, so it's going to be equal to. I will tell you, anytime you have a graph like this, let me show you this. The only time you just use a less than is if you have an open point. Otherwise, you're always using less than or equal to. For 13, well, if you look at your left side, notice the left side here is actually an arrow pointing that direction, and the right side is also an arrow pointing that direction. That means it's just continuing to get bigger. There's no starting and stopping point, so we would say that our domain is all real numbers. Our domain is all real numbers. Now we're going to go back and talk about our range. So our range is the robot part here. So robot will help us remember our range, and our range goes from bottom to top. It's also important to remember that our range is our y's. So our domain, we read from left to right. Our range, we read from bottom to top. So we're going to look at 14, 15, 16, and then we have 2 more questions over here to the side. So our range is going to work the same way, but remember we are reading from the bottom to the top. So starting at the bottom, this point down here went through -4. So we're going to write that. And then the top point went through up here at +5. And my range is my y, so we're going to put y in between there. So notice this looks just like our x did, except we're reading it from bottom to top, and we're putting our y in there. So at -4, it was a closed circle, so it's less than or equal to. And at +5, it was also a closed circle, so again, it is less than or equal to. So if we look at 15, I've got to find the bottom of my graph. Well, the bottom is here at -1. And I've got to find the top of my graph, which is at 7. So my range for this one is from -1 to 7. It is range, so I'm putting y in the middle. At -1, it's a closed circle, so I'm saying less than or equal to. And at +7, it's an open circle, so I'm just saying less than. So remember, because it had a starting point and a stopping point, what this is telling me is that my range, my y's, are in between -1 and 7. That's what this notation means. It means y is between -1 and 7. So if I look at 16, I'm supposed to find the bottom and the top. Well, notice my bottom is pointing down. I only have a top. So if I only have a top, I know I'm going to have just y, and I'm going to have my top value, which is 3. What you have to figure out, is it a less than or a greater than? Well, notice it's going down. So think about it. Is things that are down, things that are less, or things that are greater? Hopefully that makes sense to you, that it's things that are less, and because this is a completely filled in circle here, it is actually less than or equal to. So that would be my answer. we're supposed to go for these next two to go back to 11, 12, and there's also, I know on your notes it says 13 as well. We're going to find the range of these same three problems. So for 11, I'm going to draw a line through the bottom of the graph and a line through the top of the graph. So my bottom of my graph started at -3. My top of my graph was at +3, and it's my range, so I'm putting y in the middle. So at -3 down here, this bottom point, this circle was solid, so it's a less than or equal to. At the top point up here, which is +3, my point is also solid, so it's just a less than, so there's my range. When I look at 12, I'm looking at, again, the bottom of my graph. Well, the bottom of my graph is pointing down, and the top of my graph is pointing up. So that tells us this graph never stops going. It's going to continue to go on forever and ever and ever up, forever and ever and ever down. So the range in this one is all real numbers. For number 13, I'm looking for the bottom and the top. Well, there's the bottom of my graph, but it's arrows, so it's still going to keep going down. I do have a top to my graph. So for this one, this is problem 13. I know you have space for it on your notes. I made sure you did. For problem 13, I know because it only had a top, I'm just going to have y and the number. This number here that it crossed at was +4. So you've got to figure out, is the graph below that or is the graph above that? Well, notice this is easy to figure out because what direction are your arrows pointing? Your arrows are pointing down, and things that are down are things that are less than. And it is going to be less than or equal to because we didn't have an open circle there.